of the continents. And there are different types of rifted margins based on the magma activity during the breakup. They are magma rich, magma poor, intermediate, and transform. And the steady region in this talk is this shown in this black box, that is west of Iberia, that is west of Spain. And this region got separated from the Newfoundland part of the Canada. And yeah. So based on the magmatic activity, rifted margins are kind of characterized between two end members. One is called magma poor margin, and other is magma rich margins. So magma poor margins are usually show very good structure. So they are very good places to understand the tectonics involved in continental breakup. So in magma poor margins, the continental crust thins gradually, and it forms tilted. It has tilted fault blocks which end on to detachment fault, and the crust is thinned extremely in the hyperextended zone, that is the distal margin part. And there is a exhumed mantle zone where the mantle is exhumed to the surface, and beyond which is the oceanic crust. And in magma rich margins, the magma activity kind of masks a lot of structures, so we can't really clearly see what are the different structures. These are masked by structures called like seaward dipping reflectors, which are basically lava flows. And also it has a typically high lower crustal velocities, which is probably due to magmatic underplating and magmatic intrusions. And the ocean, there is no exhumed mantle in magma rich margins, and the oceanic crust is usually seen more closer towards the land. And the steady region, that is Galicia, is a magma poor margin, and we're going to see what are the structures there. So West Iberia margin is one of the very well studied rifted margin and it has contributed a lot in terms of understanding a lot of different processes happening at rifted margins. So the map here is the bathymetry map showing different seismic lines acquired in the past. The black lines are the seismic lines, and the red stars are the stars for like ocean or deep ocean drilling sites. Rifting in this region happened in many different phases. In the initial phases, there were like in basins formed in the proximal domain that is closer to the coast. And in the later phases, the rifting shifted more towards the ocean, forming Galicia Interior Basin and Galicia Bank. And in the final stages, the breakup of continent happened in deep Galicia margin. The study region for this study is shown in this yellow box called G3D, that is Galicia 3D experiment, which was performed in which they acquired multi-channel seismic data and also ocean bottom seismic data with the purpose of studying understanding rifting in 3 dimensions. So the details of Galicia 3D experiment are here. So the multi-channel seismic data was acquired using Marcus Langseth, and the OBSS ocean bottom seismometers were deployed with Poseidon, that is a German ship, in 2013. And the white lines here are the shooting lines. Multi-channels is the source lines, shooting lines. 100 shot profiles were shot, and with a shot spacing of 37.5 meters. The multi-channel data was recorded with the 4 6-kilometer long streamers, and the OBSS recorded the same signal sitting on the ocean floor. The OBSS in green color are the ones which were used for FWI, and also the ones in pink were used for FWI, and the one in yellow were not used because they had some data problems. And the OBSS in the top line were not used because of larger uncertainty in their locations for FWI. However, they were used for travel time tomography. In the section below, this is the time migrated section of the time migrated section from the 3D volume, where I'm highlighting different different geological packages. So the dashed blue line is the top of the basement, below which is the pre and synrift sediment packages, that is the sediments which were deposited at the time of continental breakup. and below the dashed red line and the dashed black line is the continental crust, and below which is a detachment fault that is a very thick, a very strong reflector on seismic sections, which is also the boundary between crust and mantle, called the S reflector in this region. And on towards the ocean, towards the sea side, we have a periodite ridge that is exhumed mantle, that is the mantle exhumed to the surface here, and it's called periodite ridge. For this study, we formed a grid. The dashed red line is a grid for FWI, and the dashed black line is the grid that was used for processing the multi-channel seismic data. This figure is for showing the seismic data recorded by the ocean bottom seismometer along one of the profiles, and we can see very clearly refractions, wide angle refractions from the S reflector, and also from the crustal arrivals, PG arrivals, and we see very strong direct arrivals. And also we have a very good because of the very deep seafloor, we can see very clearly the first order multiples, which are quite separated from the direct arrivals. And also we have noise from the previous shot. So yeah. So a brief geological background of Deep Galicia margin. This is a figure. This is a figure from the 3D seismic volume, and towards the west is the ocean, and towards the east is the land. And we have different packages marked in different colors, and ABC are the pre-syn rift packages, and the crystalline basement, that is the crust at the time of rifting, is shown in pink, and below the crust is the mantle separated by S reflector, that is the detachment fault in this region. And yeah, there are the fault blocks, the faults which are cutting through the crust, that is from the top of the crystalline basement to the touching the S reflector. And these faults during the time of rifting acted as fluid pathways, that is once there was ocean on the top of it, the fluid traveled through these parts and went on and reached the mantle, serpentinizing the mantle. Yeah, so based on the corrugations on the S surface, that is and corrugations on the S surface and on the corrugations on the fault blocks, it was proposed that the fault blocks rotated on the surface on the top of the S reflector. And one of the very strong debates about the rifted margins, I mean, the hyperextended crust, is that when we try to reconstruct the crust based on the fault activities, we don't see the full reconstruction. The full crust is not able, we cannot completely reconstruct the crust. And there are different theories proposed to explain that. One is called polyphase faulting, and other is sequential faulting, which are at the center of the discussion. But however, I'm not going to go into details of them because that is out of scope of this talk. So, and this is one of the debates, and there are many other debates. So in order to answer questions related to rifted margins, we proposed to do a high resolution velocity modeling of this region using the ocean bottom seismic data. And we use the technique called FWI, that is full waveform inversion. So traditionally, conventionally, it is for generating the velocity models. Travel time tomography is a common tool in academia, in which only travel time information, that is the arrival times, are incorporated into inversions. While in case of FWI, which is a higher order inversion technique, the information of the amplitudes as well as travel times is incorporated into the inversion to generate high resolution velocity models. So FWI is a iterative process in which it iteratively minimizes the objective function, that is the difference between the field data and synthetic data. It is a higher order imaging technique, so it requires a starting model that can predict the data accurately enough, and travel time tomography is usually good enough as a starting model for FWI. And the model update is calculated by performing cross correlation of the forward wave field with the residual wave field. So the cartoon here shows how the model update is calculated. So the yellow star is a source, The green triangle is the receiver. So we calculate the forward wave field, which is propagated to the subsurface and is recorded at the receiver. We calculate the residuals by computing the difference between the observed data and forward model data, and the residuals are back propagated. So, and we cross correlate these two wave fields, and we get a model update for the next iteration. So we can see here that it's a quite demanding, computationally demanding method. Like we are required to calculate forward modeling and also residual field and then cross correlation. So there is a huge amount of memory and computations happening at each pair of source receivers and in each iterations. And also it is a highly nonlinear technique. That means the inputs and outputs are to change in the input is not proportional to the change in the output. Suppose say you change the input a bit, you may not see any change in the output, and you further change the input a bit and you may not see anything change in the output, but you change it further and things may fall off the cliff, like it may change completely. So it's a very highly nonlinear technique. One of the classical problems in FWI is cycle skipping, in which it happens that different wiggles, the different order wiggles are matched by FWI. So cycle skipping is demonstrated here using this figure, like in which the dotted trace is a synthetic trace, and the solid trace is the observed data set, and the lobes are marked with the order of the lobes are marked as n-1, n, and n+1. So the basic aim of FWI is to match the nth lobe with the nth lobe of the observed data. But however, if the difference between the two lobes is like say more than half a cycle, in that case the n+1 will probably will be matched with n, and that will lead to a wrong result, and it is called cycle skipping. The problem of cycle skipping is sorted in case of the bottom two traces. This is again the observed trace, and here it is the synthetic trace. In this, between these two traces, the difference is not so much, that is not less than half a cycle. And in this case, FWI will kind of converge the nth lobe with the nth with the right lobe, and it will lead to a right solution. FWI has a lot of many different key ingredients, and I'll be talking about them, each of them. The first important thing is the starting model, and in our case, we have the starting model developed from travel time tomography of first arrivals, and we check the ability. I mean, it's important that the starting model is able to predict the data within an acceptable range. Otherwise, that may lead to cycle skipping problem. And another important thing is the starting frequency, that is at what frequencies we start the inversion. And for this, we use something called phase plots, which I'll be showing in the next slides. And also we performed some synthetic test runs, not synthetic, actual data test runs using a subset of the data set, and decided what is going to be the starting frequencies. Another important thing is the wavelet. Wavelet represents the source, and we developed the wavelet using the direct water arrivals and by designing a Wiener filter, using which we developed the wavelet source. And the data which we inputted into the inversion is just refraction data recorded by the hydrophones. So that is just acoustic signal. And we applied a simple bandpass filtering to the data with the rolling of frequencies at 3 and 5 hertz. Yeah, the inversion strategy is that we performed acoustic full waveform inversion, and the frequencies we inverted were between 3 and 5.2 hertz, increasing in steps. And the model size in the east-west direction is 78 kilometers, and in the north-south direction it is 22 kilometers, and depth of 12 kilometers. Grid spacing in all the 3 dimensions is 50 meters, and we applied some smoothing to suppress the artifacts. At each frequency, we performed 30 iterations. So in total, we performed 150 iterations. So for the source wavelet, we had a workflow for the source wavelet. So initially, we took a random guess wavelet, and we have taken the water column velocities, and we generated a synthetic trace. And then we tried to match the synthetic trace with the observed data. For this matching, we calculated the inverse of the synthetic trace and performed the convolution between these two, and that gives us a filter. And we applied this filter to the guess wavelet, and that transforms the guess wavelet into the source wavelet that is capable of predicting the data. Starting model was obtained from travel time tomography. Here again, in this profile, the yellow dots are the OVSs, and the interpretations are the top of the basement, top of the crystalline crust, and the S reflector mark from multi-channel seismics. And it's a smooth model derived from using first arrival travel time tomography. As I said, it's very important that the starting modeling should be able to predict the data within good accuracy, that is within half a cycle. So here to test that, we plotted the observed data and synthetic data in a set of 10 traces adjacent to each other. So the observed data is highlighted in the colored band, whereas the synthetic is not highlighted. And this kind of shows us the alignment between the observed and the synthetic data. And we see that it's quite good. It's within the half a cycle. And I'm showing here two profiles from an OBS. So for the starting frequency, we plotted some, we used something called phase plots. So in the figure A here, we are showing the phase plots for an OBS. The OBS is shown, the OBS location is at the center, is shown using a star here, red star. And around the OBS, this is the top view of the OBS. And around the OBS, this blank space is because we removed the direct arrivals. And these are the refractions. And at each short location, that is at each trace location, we extracted just the first arrival, and we're using a Gaussian window, and we applied Fourier transform on that and extracted the phase, calculated the phase, and plotted them. So the concentric nature of this phase changes of the first arrivals indicates a very good signal to noise ratio, which is essential for FWI. And we can see here that as the offset increases at around 15 kilometers, the dots, they becomes more chaotic, indicating that it's not a good quality data. And we did the same phase plots for at 2.7 hertz and 3 hertz. It's basically to choose the starting frequency. And we also performed, we also plotted the phase plots for synthetic data at the same OBS, and also calculated the residuals by subtracting observed and the synthetic trace at 2.7 hertz and 3 hertz. So we see the residuals are kind of like close enough, like the RMS of the amplitude phases is like not much different for 2.7 and 3 hertz. And it is mostly like greenish, bluish green, that is somewhere here in this region, which is within half a cycle. So that is there, it's good. Like the inversion can be started from 2.7 hertz and 3 hertz. Either of the frequencies is fine. But however, the fundamental notion to start an inversion is that start it as low as possible so that it avoids cycle skipping. But that would mean that more computation time and extra sources. So in that case, we did a synthetic test. The results of this are not showing here in this publication here cited here. And we decided to go with 3 hertz because there is not much difference in the synthetic test, starting an inversion from 2.7 and 3 hertz. So we use the phase plot residuals again to also perform quality control, and quality control is a very important thing for FWI. As I said, it's a highly nonlinear technique. So we use phase plot to track the phases during the inversion. So here in the first A plot is the residuals of the phase residuals with the starting model, and in the C is the phase residuals after the first iterations at 3 hertz, and this is the phase residuals at the end of the inversion, that is with the final model. And we can see the change in the colors are gradual, like say from somewhere around bluish green to mostly green, which is the 0 phase. And we did this also at the 4.5 hertz to see that, and also it's the same. But however, at 4.5 hertz, we see there are certain locations where the changes are abrupt, like changing from red to blue, that is from pi to minus pi, which indicates that they are probably cycle skipped. But however, these same regions at 3 hertz are not really cycle skipped, because we can see again the change is gradual. So this clearly indicates that the advantage of starting an inversion from lower frequencies. Another quality control is that, again, plotting the synthetic and observed traces in a set of 10 traces. The observed traces are highlighted in the color, and we can see here the travel time. Here I'm showing the predictions, the comparison with the travel time model and the FWI generated synthetic data along a profile from an OBS, two profiles, that is profile 1 in AC and profile 2 in BD. And we see that with the travel time model, there are small mismatches, but they're within the half a cycle. Whereas with the FWI, it aligns pretty well with the observed data. It has improved a lot. And yeah, it's in the same, also the same in this case, like there are small mismatches. Whereas in this case, I mean, with the FWI, it kind of improved it a lot better. So this kind of tells that the FWI has done a good job. Another step to validate our full waveform inversion model is comparing it with the multi-channel seismic volume. So this is a time slice from at a depth of 9.1 seconds, that is 100 milliseconds below the S reflector depth average. And we overlaid our velocity model on top of it. And we can see that there is a very clear velocity clear jump that aligns, velocity change that aligns very well with the S reflector here, which kind of tells us that the velocity FWI constrained the velocities pretty well below the S as well. And also, if you can see that within the blue color is crystalline crust, and we can see that there are reflections here in this here, and which are very well constrained again by the FWI model. So this kind of validates our results obtained by FWI, 3D FWI. So coming to the comparison between 2D and 3D FWI results. So in academia, sparsely spaced OBS data sets are quite common, and they are 2D data sets are very common, and they usually use it to generating smooth velocity models. FWI is rarely performed using those data sets because the problem of data sparsity can lead to converge to a poor wrong result. So in this case, we performed using a sparse data set. We performed 3D FWI, and also we performed 2D, and we tried to highlight the difference between 2D and 3D FWI using a sparse data set. So for that, what we did was we used data from instruments which are shown within this black box and highlight black box. And for 2D case, we have used the green data from the instruments shown in green and pink, and we have just used the two shooting profiles directly above them. And for the case of 2.5D, we use the data from the same instruments, but with all of the shots. And for the case of 3D, we have used the shots from all the green instruments and also the pink ones, and all the shots. So here, in this case, like again, these are the time converted sections of the velocity model superlaid on the multi-channel seismic data. So interpretations are marked on the top of the multi-channel seismics. The blue dashed line is the top of the post-strip sediment. That is, these are sediments, and these are the base of it. And these are the packages, pre and syndift packages. And below it is the crystalline crust. And the black dashed line is the S reflector, and here is the periodicite ridge. I'd like to take your attention to particularly to the crystalline crust, that is between the dashed black line and the S reflector. In case of 2D, we see that this section is kind of like has circular features, and also the base has a lot of undulating features at the S reflector. And if you see that the same region within the 2.5D, it becomes kind of like more smoothed out, and it kind of follows better than the 2D. And also the undulations at the S reflector are less. And in case of 3D, if you see that this section is kind of like matching pretty well with the multi-channel interpretations, and also the S reflector has become very well constrained in case of 3D. Yeah. So one of the major advantages 3D has is that it constrains. Oh, sorry. Yeah. So this difference in the circular features is probably due to the data sparsity, that is very sparse data, and also very less amount of data in 2D, which results in a very poor constraints on the inversion problem. and results in this circular features, which are artifacts. Another advantage which 3D has is that uh, it can constrain the structures which vary in 3 dimension. In case of 2D, it assumes that the structural variation is only in the dip direction, and along the strike direction, it assumes it's constant. There is no change. Whereas in settings like rifted margins, where the fault blocks have great significant variability along the strike, this problem can be a big one. And especially in case when we are using a sparsely spaced data set like OBS data set, these assumptions can become exaggerated. All in all, the thing is, like, 3D data set mitigates the effect of receiver sparsity in FWI imaging to a certain extent, at least. Another important aspect is the data fit. Like, we plotted the data residual plots. Those are obtained by subtracting the observed data with final model predicted data. In this figure, I'm showing data residual plots for 3 OBSs, that is OBS 45, OBS 46, and OBS 38. And for the 3 cases, that is 2D case, 2.5D case, and 3D case. For the first 2 OBSs, that is OBS 45 and 46, the differences are kind of like quite close. There is not significant difference, which makes it difficult to decide which OBS which is kind of like performing better, which it makes it very difficult to decide which inversion is kind of better. But however, in case of OBS 38, we see that the OBS 2D inversion is kind of fitting the data pretty well, much better than the 3D case. There are very strong reflectors, very strong arrivals in case of 3D residuals, which we can see. This is surprising because 3D is usually expected to fit better than 3D, because it's the real world is a 3D case. In this case, it is an interesting and a point to note here is that the OBS 38 has higher uncertainty in its locations because of the large misfits, large large time shifts in its arrivals. So the OBS locations are calculated by using the water wave arrival. So when we are acquiring the data, the OBSs are let to freely fall through the sea surface, through the water column, and they go and sit on the sea floor. And once we recover, when we recover the OBSs from the ocean bottom, we try to estimate their locations by using the arrival times of the direct arrival. So if there are time shifts in the direct arrival, in that case, you will have large uncertainties in the OBS location. So OBS 38 had very large time shifts, so it had larger uncertainty. So in that case, we actually expect very long, strong residuals, which we can see in 3D case. But whereas 2D is kind of like fitting it pretty well, so we kind of interpret it as that 2D FWI is overfitting, and that is because 2D FWI has lesser constraints in case of sparsely spaced OBS data, and whereas 3D has better constraints from instruments which are out of the line as well. So in more data. So in that case, it doesn't allow the inversion to fit to arrivals that are not really matching, whereas in 2D, less constraints, and it fits more, overfits the data. And another interesting aspect is the deeper imaging. So the figure here shows the locations of the OBSs in yellow with their numbers on it. And again, the interpretations are same as the previous slides. And these are the velocity perturbations obtained by subtracting the final model with the starting model. So one interesting anomaly is that the anomaly below the S reflector, that is the dashed line, the blue one here, which is marked in the black arrows. And if you see from 2D to 3D, this anomaly below the S reflector is kind of like extending. And this kind of indicates that below the S reflector, the 3D FWI has better constraints, and it was able to kind of like invert. It was able to kind of like constrain the structure's velocities pretty well below the S reflector. All these anomalies were kind of like recovered in a synthetic tests, which are given again in the publication cited here. So in this case, so in deeper sections, 3D FWI has stronger constraints at deeper depths than 2D FWI. One important interesting aspect which I want to show as in this talk is that so in 2000 and Scuba et al. 2019 has kind of generated and velocities below the S reflector using a machine learning algorithm. So in that case, what they did is that they used the velocities along a 2D FWI profile, and they used input features from the 3D seismic volume, and they tried to kind of like predict based on the they tried to train the algorithm in such a way that they try to predict the velocities over the complete volume using the velocities from the 2D line. And these are the velocities from Scuba et al. And here are the velocities in the figure A from 3D FWI. And the black solid lines are the fault intersections, that is the locations where the faults are touching the S reflector. And surprisingly, we see that there is kind of hardly any match between these two maps. So which map is kind of correct map? So I think it is the FWI map, because the FWI map actually makes more sense and it shows more alignment with the fault intersections. And not just that, the 2D FWI velocities which were used for the training the machine learning algorithm were probably not really strong, didn't have strong constraints below the S reflector, as I have shown in the previous slides. So the velocities are probably not correct. The velocities predicted by the machine learning are not correct, probably. And another thing is that when we compare the thickness of the crystalline crust, it shows very good match with the multi-channel, with the machine learning algorithm things, because we can see that here this structure here has a very thick crust, and again here this section has a lower crust, and this section has a lower crust. So this is a very good kind of correlation, and this is one of the input features to the machine learning thing. So probably it is the machine learning algorithm was too much inclined to one of the inputs as well. So all in all, I would say that the 3D FWI result is much better than the machine learning algorithm predicted velocities. Finally, this brings us to the last section of the talk, that is mirror imaging. So traditionally, multiples are not used for for any imaging. They are just ignored because they're considered as noise. Whereas in case of OBS data, these multiples can be used for generating seismic images. And also, OBS data is usually used only for generating the velocity models, and they're rarely used for generating images. But however, using the mirror imaging technique, OBS data recorded by the OBS and up to the multiples, we can generate a seismic image of the subsurface. So the cartoon here shows the different arrivals, basically 3 arrivals. One is the primary waves, that is traveling from the source shown as red star, bouncing off the subsurface and recorded at the OBS, which is shown in the yellow triangle. And there are 2 multiples, that is the water column multiples. One is bouncing off. One is called as a receiver multiple, and one is called as a source receiver multiple, and other is called the source multiple, because the source multiple bounces off closer to the source, and the receiver multiples are bouncing off at the closer to the receiver. So these 2 multiples have a slight difference in time, but however, depending upon the impedance contrast at the sea floor, one of them is very dominating. So in the case of rifted margins, very low impedance contrast at the sea floor because of the sediments results in the receiver side multiple to be very strong than the source side multiple, very dominant. So we don't really require any processing to separate them out, because one of them is very dominant. And in mirror imaging, what we do is that we just try to take an image, we try to reflect the ocean bottom seismometer with respect to the sea surface, and say that it is exactly at twice the depth of the sea floor, and we say that this whole of this region is a sea column, water column. So in that case, by doing this small change, we can treat the multiples as just primaries. Like, see, it's just bouncing out of the surface. It's so yeah, using this small change, we can apply migration algorithms on the multiples and generate the images. So here is the section which shows the image which has been developed from OBS data, purely OBS data, no multi-channel recordings. And this is the section from 3D multi-channel. So this comparison in a way is not really fair, because this is too much of data recorded by too many number of receivers and shots. And this is from a very sparsely spaced OBSs. And yeah, however, in this case, we applied Kirchhoff time migration, and we used a 3D travel time model, velocity model. And it's we can see that within the sedimentary section, we can see quite a number of, we can see good reflectors which are comparable with the multi-channel. And also the top of the basement is kind of like pretty well imaged in the mirror imaging. So yeah, maybe the deeper section is very weak signal, so it's probably not very well imaged, but still we can generate an image using just OBS data. And yeah, and we also performed the depth migration of the same, and we can see the same structures. And we also performed depth migration using just the primaries of the OBS, and we don't see much structure because the primaries have very less lateral coverage of the subsurface. They just bounce off from one location, so they don't really generate a very continuous image. So the summary for today's talk is that the difference between 2D and 3D FWI results can be significant when we are using a sparse data set, with 2D FWI generating more artifacts than 3D. 2D FWI can be prone to overfitting using a sparse data set. And also 3D FWI has a stronger constraints at deeper depths. And at the end is the OBS data from OBSs can be used to generate seismic images using mirror imaging. Oh, sorry. Thank you.
Thanks, Bhargav.
Yeah, thanks.
Very interesting talk. Thank you. And
thank you.
What was interesting for me is that you used a lot of techniques which are very common here in the oil industry. So yeah, I have used mirror imaging for the shallow structure in some parts of the world for imaging the very shallow structure, and that definitely gives a very high resolution and a good lateral coverage because of multiples. You get twice the resolution than the primaries, and of course, that was very interesting for me. And other thing is that FWI, it is picking up. We have Dr. Sen here, who has been doing it for, I think, for ages now. It is expensive in oil industry. It is being used. It is picking up quite a bit. We go to much higher than what the academia you were trying to do because of the resources available. Very interesting.
Thanks.
I will open it up to questions. Anybody has any questions? Thank you again.
Thanks.
You can unmute yourself and ask a question, or you can put it in the chat box. I think Subhashis ji had to leave because he had some other commitment. And Dr. Sen, your comments are welcome. I saw you were busy with other meetings. So
my meeting ran over time, so I just was a little late. But I've seen, at least most of this talk at DTIG. But a couple of quick comments. It's very good talk. Anyway, it's very good work. Excellent work.
Thank you.
So when you have this marine data set and you're deriving wavelets, so typically in academic data set, we notice this, bubble pulse in the so was it? Did you do a designature decon? Or?
Yeah, that's a very good question. Actually, we did not actually, because it's not. It's actually something. It's not exactly a source. We would say that it's something which can predict the data in the in our case. So we did this, followed this, we came up with this wavelet, and what we did was we tried to just predict the data, check it, like if it is able to predict the data, and then after that we were like happy, like it's okay, yeah, it's predicting the data. But yeah, in to be very ideal, yeah, we had to do that bubble, removing the ghost thing. Yeah.
Yeah, and the reason I was asking this is because when you showed the wavelet, it does not show any bubbles.
Yeah.
Maybe they'd already designated that. I don't know. Could be that they'd already did that in the data. I don't know. But
Yeah.
you better.
Yeah, probably. Yeah.
And one other thing is that you were you had that image where you show like an image with multiples and without multiples. Can you go back to that slide? I had
sure.
Maybe I missed something.
This one?
There was another one.
This one?
Yeah, so what happened here in the lower plot, you don't see those flat layers?
Because the OBSs are, the primary signals don't really cover the subsurface laterally very well. So they just bounce off from one location.
Right. Yeah. Okay, so you're not seeing any of that stuff. Okay.
Yeah.
Okay. Makes sense. Okay.
Yeah.
Yeah, but overall it's good, very good image.
Thank you.
So then, the depths are different, right?
Sorry.
Just I'm trying to correlate this section with the one on the top.
The depths are, yes, I think the depths are similar. Yeah.
So you have some kind of a diaperic structure
here. This one?
No, in the bottom one. Is this the same line or?
Yeah, it's the same line. It's the same 2D line. Yeah.
Okay. So yeah, for example, if you go bring your cursor more to the right in the lower figure.
In the lower figure, yeah, here.
Yeah, a little bit more. Yeah, a little bit more. Yeah, so you see that structure here?
Yeah.
And where is that? Yeah, so what is that structure in the upper figure?
I think this is basically the data gap, like because of the primaries are not really imaging this part, whereas the structure here is there is this structure. This is basically a continental block, and yeah, so this is the S reflector which is touching it. So here it is. The primaries are not really doing a good job. I mean, because they don't have that lateral coverage.
Really, that's a big difference. I wouldn't expect that.
Yeah.
Okay. Good.
Thanks, sir.
Good to see Paresh here.
Yeah, very good work.
Thank you.
Yeah, I enjoyed listening to you. I have one simple question.
Yeah.
You have shown 2.5D.
Yeah.
What actually you mean by that in this case of SASB? I heard it from and all those.
So it is basically like when we use we are using the instruments along one line, and we are just using the shots from all the from a whole of the volume. So how it is different from 2D, 3D is that in 3D we have instruments also which are there off the lines, so that constrains the 3D inversion pretty well in also the lateral direction. Whereas in 2.5D there are no constraints. There are constraints from the shots, but there are no constraints from the receivers in the lateral direction.
Wait a second. So you're saying that in 2.5D you are using the sources from outside of the line?
Yeah, the whole of the volume.
But that's 3D. 3D, but
it is 3D, but
in one line.
Along one line. Its receivers are only just along one line.
Okay, so but the way actually 2.5D is used commonly is when you have 2D data with 3D corrections, because when you basically constrain your 2D, the real Earth is 3D, right? The way propagation is 3D.
Yeah.
But if you use a 2D theory, and 2D line to migrate or model or image or FWI, then you're essentially assuming a line source.
Yeah.
Okay.
Yeah.
And 2.5D, what it does, it corrects the line source to a point source approximately.
Yeah.
So what happens is that in 2D, if you put in a delta function as the source,
yeah,
then let me draw it on the board here if I can.
I'll stop sharing the screen.
Okay. Let me see if I can. Can you let me share my screen, Sanjay?
I think you should have permission now.
Well, it's not allowing me to do that. Oh, okay. It says one participant can share at a time.
I stopped sharing.
Okay. Okay, so can you see my whiteboard now?
Yeah.
Everybody?
Yeah, we can see your whiteboard.
Okay, so when you assume 2D, but actually the Earth is 3D, then you are assuming cylindrical symmetry. That means, the structure is the same in all directions.
Yeah.
Okay. And in the modeling, you say that it's a point source. In reality, it's a point source. But when you take your 3D wave equation,
yeah,
and then turn it into, say, delta P is equal to V square del square P. And then if you make it like del X square plus del Y square, essentially you are approximating this as a line source. Okay.
Yeah.
So if you put in a zero phase wavelet, okay, I didn't draw it correctly. In 3D, if there is no attenuation, it will propagate the same way. But in 2D, what happens is that it actually decays. This is t to the power minus half decay.
Yeah.
Another thing is that your spreading is square root of r.
Yeah.
Rather than r. So in 2.5D, you actually convolve it with a wavelet that makes it look like a symmetric zero phase wavelet.
Yeah.
So
yeah.
corrects for 2.5D and corrects it for spreading. So that is the difference between 2.5D and 3D. That is how we commonly use.
But
so, yeah, it's a little different. So what you're calling 2.5D is actually 3D, but along a line.
Yeah.
Okay.
Well, in my case, we kind of suppress the amplitude effects because our objective function is
right.
Like it's not trace normalized.
Yeah, yeah.
Because so it's mostly like it's predominantly phase inversion. So
yeah.
So the difference because of this wavelet changes is probably very minimal.
Okay.
Yeah.
And also ignoring amplitude, so square root of r is not important here. So.
Yeah.
Okay. Yeah, but the main reason I wanted to tell you this is because this is what is called 2.5.
Yeah, it's very, very useful. Yeah. Yeah. Thank you for that, sir.
Yeah, no problem. But I understand what you're calling 2.5D. So did I stop sharing or not?
No.
I'm still sharing it?
Yeah.
Let's see. How do I stop that? Okay. Yeah.
Yeah.
Thank you, Professor Sin sir and Bhargav for explaining.
Thank you for the question.
So another question, like you are doing cross correlation. So when you are doing cross correlation, so you are doing with one trace at a time, or you're taking entire waveform, and I could not understand that.
For the 3D case, it will be full the complete wave field.
Complete wave.
Yeah, the complete wave field will be stored, and then we calculate the residuals, and that is also stored, and then we do the cross correlation, and then it is done for each OBS. I mean, each OBS and source. Each OBS, like we applied data reciprocity. That means the OBSs are treated as sources, and the receivers are treated as the sources are treated as receivers. So, and we applied each OBS to a node. So all these operations are for concerned with each OBS are performed in one computation node, and at the end, all the correlations are kind of merged by a master node. And yeah, so these are the details of how the computation is been carried out.
So did you do a frequency domain?
It's a time domain. I'm sorry.
Time domain, then you filter it, and then basically your objective function is in frequency domain. Is that what you're saying, or?
No, my objective function.
So you basically filter the data in a particular frequency band.
Yeah. So well, we did it in time domain, but we filtered the data out from like only we taken like frequencies which we are interested. Because being with such a sparse data, we didn't want to risk of going into higher frequencies.
But unlike frequency domain inversion, you can't really be having one frequency in the data.
Oh, that is a low pass frequency which is rolling off at that frequency. Right. I'm sorry about that.
That's okay. Yeah.
Yeah.
So Bhargav, what was the nominal spacing of your nodes, the OBS stations? What was the average spacing?
It was 3.2 kilometers along the line.
Okay.
And across the lines it was 6.5 kilometers.
Wow, that's very sparse.
Yeah, it is quite sparse.
Okay.
Yeah.
Okay. Thank you. Okay, I had allotted 1 hour. If there are any questions, so you are welcome to ask. Otherwise, we will thank Bhargav for this wonderful talk, and we'll close the meeting.
So Sanjay,
Aurab or Tanesh, any students have any questions?
Sanjay, you didn't broadcast the meeting information very much, right? This time, or what happened? There were so few people today.
I think Ganesh Chaturthi is having an effect on our attendance today.
Oh, okay.
I circulated among Kharagpur students. Some of them have joined.
Okay.
Yeah, our Dhananjay, Abhijit, these people are also busy with something else. So something important at BP, I think.
Yeah, looks like BP guys are not here today.
Yeah.
I guess this is the recording, so you can post the recording for people.
Yeah, we will do that. Yeah. Sure. Okay, then I think that's it. Thank you everyone for joining, and thanks Bhargav for giving a wonderful talk. We wish you all the best.
Thank you very much.
You are at a very good place and very good people. So we wish you a lot of success in your future life and career.
Thank you very much.
Bye.
Bye-bye.
Thank you everyone for this informative session.
Thank you.
Thank you. Bye.
Bye-bye.